Hello, this is going to be a little example that I'm going to show you how to do some coding of these Bravais lattices for your assignment. A few people have asked. So what I'm going to walk you through is how I would approach coding up one of the first lattices that we looked at, which was the simple cubic lattice. So right now I'm sitting at the command line. I'm using OS X, but everything should work just as well in Python, or if you're using something like Cygwin, or you're logged into an external machine, it's all basically the same. And the editor that I'm going to be using today is called VI, but you could just as easily use something like a text editor like Notepad, or if you're using OS X, you could use TextMate, just something that I can write code in. So, hello, this is the thing that I'll be writing code in, and then this is where I'll be running. Okay, so actually I changed my mind. Do I want to use VI, or do I want to use a Notepad? Yeah, we'll use VI. Cool kids use VI. So, right. Just to make sure that I'm in the same directory here. So pwd is present working directory. That's just so I know where in my file system I'm sitting. Okay, good. So in this window, over here, this is where I'll be running Python, and over here, in this window is where I'll be writing stuff. So I'm going to create a file called scc.py, just to convince you that it works. I'll start off by going print hello world. I'll save it, hit ls over here, and I can see that that file has been created. So to run it, I simply type python scc.py. It runs, and now it prints my output, hello world. Okay, so let's now start altering our source code so that we can actually produce a simple cubic lattice. Probably the best place to start is with the loops, just to show you how this is going to work, and then afterwards we'll worry about getting it into a file. A simple cubic lattice has, as we discussed, lattice vectors that are equal to, A1 is equal to 1, 0, 0. So this is a lattice vector that points in the x-hat direction. A2 is equal to 0, 1, 0, a lattice vector that points in the y-hat direction. And A3 is 0, 0, 1, which of course points in z-hat. The way that you can generate a Bravais lattice is through, as we said in class, r is equal to, don't worry about coding this for a moment, this is just a way for me to write down the notes. It's some integer times a1 plus another integer times a2 plus another integer times a3. By cycling through whole numbers of n1, n2, and n3, I can produce the Bravais lattice from these guys. So what does that look like in practice? Well, so let's just, the useful thing about Python is you can actually do a trick, which I'm about to show you here, is you can use the interpreter. An interpreter lets you test little pieces of code as you work. So I'm going to open Python here, and I'm going to test something. I'm going to take this bit of code, because I can't remember a detail, and I'm going to say something like this. So I say A1 is equal to this, and A2 is equal to that. And the thing I want to test is, am I able to just add these two things? Well, how will Python deal with that? Right. And this is what I remembered. Python, because these are lists at the moment, if I go A1 plus A2, what I get is this thing right here, which is a longer list, right? So this is the first part of the list, and this is the second part of the list, which mathematically is not what I expected it to do, which is why it's useful to test some of these ideas in my interpreter, because I didn't have to write a whole code around it. I could just check this one feature. So how can I deal with this? Well, there's two ways that you can deal with it. Just for completeness, I'll show you what one of them is. So import numpy as np, and then I'm going to say a1 is equal to np.array of a1. This is going to convert the list into a mathematical array, a numpy array, And then the properties of addition will change for these lists, and I'll show you what I mean by that in a second. So here, A2 is now equal to np.array of A2. Now let's test again to see what happens. A1 plus A2. Ah, okay. You'll note that the behavior is different. Previously, A1 and A2 were lists, and when you add two lists together, you get a longer list. Then I converted them to NumPy arrays, and when I add those together, I get a mathematical object that behaves the way that I expect it to. So knowing that, why don't I do this? Rather than start these things off as lists, I'm going to work with NumPy. Now, if you try this on your own computer, you might find that it says something like NumPy can't be found, which means you have to install it. If you're in that case, don't worry. There's another way around this, and I can show you later how to install NumPy. NumPy is an external library. It's a particularly useful one for computation, but it doesn't necessarily come installed when you get Python to begin with. So rather than initialize this as A1, I'm going to initialize this like this as a NumPy array. And then this one, I'm going to do the same thing. And then again here. Okay, so these are three lattice vectors that are similar to the ones that we talked about in class. Now this R is going to produce these different positions, right? And we said that I cycle through different integers here, n1, n2, and n3, and I multiply by the lattice vectors. So how do I cycle through something in Python? Well, we use loops. And there's different types of loops that you could use. So you could use a while loop, or probably the one that makes the most sense in this case would be to use a for loop. So simply because it's more compact. So let's do the following. For I in range, we'll say 3. So this is going to produce values 0, 1, and 2. 1, 2, 3, 4. I'm going to go for j in range 3, which again will produce 3 values. 1, 2, 3, 4. The reason I'm counting to 4 is normally in Python, when you go in from a for loop, the standard is you do 4 spaces. 1, 2, 3, 4. For a in range 3. And then finally, 2, 3, 4. Okay, so the reason I did ijk is because that's typically what people do as a for loop. But then I just realized that to make my code a little bit easier to read, I should probably go for, let's go for n1. This is going to go for n2 and for n3. So this will cycle through the values of 0, 1, and 2 for n1. This one will go 0, 1, and 2 for n2. And this one will go 0, 1, and 2 for n3. And let's just convince ourselves that that's actually what's going to happen here. So I'm going to comment this out. I'll go 1, 2, 3, 4. And I'm going to print n1, n2, and n3. I'll save this code. And now I'm going to run it over here. Let's see what it does. Okay, so it spit out a whole bunch of text. Actually, so much text that it went past the window. So what I can do to see the text is, rather than just have it print out all at once, I'm going to use this little symbol here, okay, which is a vertical bar. So normally it's sort of, it's around your enter button on the right-hand side. You might have to hit shift, and I'm going to do something which is called piping into more. This is an optional step, but it just makes it a little bit easier. So it'll show me a page of data, and then if I hit space, it'll show me the rest of it. So this is the output. So it starts 0, 0, 0. Then it goes 0, 0, 1, 0, 0, 2. And then once it hits 2, then this initial for loop, which for loop are we doing at the moment? This for loop, right, because we go from the inside out, this for loop here is now done. And when this is done, it goes out to the next level, right? And it'll restart. So it'll go 0, 1, 0, 0, 1, 1, and so on. And it goes through every one of these for loops. Okay, so those are the values of n1, n2, and n3. So now I'm going to remove that print statement. and I'm going to set the value r equal to this, just like we did in class. Now let's print out r. I'll save this again, and I'm going to run it again, where notice I'm piping it anymore, and let's see what the values get. Okay, so I print out 0, 0, 0, 0, 0, 1, 0, 0, 2. So in some ways, this sort of seems like a silly step, right? Because I haven't really done anything useful at this stage. It seems like this, dealing with this R business and the A's has not given me a result that's any different than what I had before. But why don't you consider the following? Have a look at this. Rather than using, I'm giving you more than I said I would, rather than just using a simple cubic lattice, let's see what I do when I have a different set of lattice vectors. So I'm going to comment out these, I copied them, and I'm going to comment these ones out. And now I'm going to use a set of lattice vectors that look like this. So half, half, 0, half, 0, half, and 0, half, half. Just clean up these formatting. There needs to be 0 there. Let's see what this looks like. Okay. Clean it up so that you can see exactly what I'm doing. So now, rather than having lattice vectors that are just one along the diagonal, now I have lattice vectors that are given here. And if you remember, this corresponds to one of the Bravais lattices that we talked about in class. One just quick note, as you can see, I'm filling in decimal places on all these values here. There's a reason for this. Python makes a distinction between integer math and floating point math. And sometimes integer math doesn't operate in the way that you'd like. So for instance, and this should have been covered in the tutorial, if I go 1 divided by 2 in an integer, Python will floor that to 0. But that's not the behavior that I want. So I want to operate with floats. And the way that you do that is you simply put a decimal beside all of these guys. This already has a decimal, right? 0.5, so it's automatically a float. Okay, so what I've done is I have commented out this row here. This was my simple cubic row. And this now is either a BCC or an FCC. And we can figure that out once we visualize it, which one it is. And I'm keeping this part of the code the same, and I'm keeping this part of the code here the same. So I'm going to save it, I'm going to print out R. Okay, so I run it again. And now you can see that what gets printed to the screen looks very different than before, right? With the simple cubic, it was just 0, 0, 1, and then it was 0, 0, 2. But now what I'm doing is I'm actually printing out, the first one is the same, but I'm printing out 0, 0.5, 0.5. So this is the first coordinate in this different lattice. I've changed the lattice vectors, and now I've keeping this part. The algorithm is the same as it was before, but I have a different set of coordinates that are popping up. All right. Now, printing to a screen is not a particularly, well, it's useful for debugging, but it's not what we want to do to actually visualize a file. So I'm going to modify my code now so that I can produce a useful file that we can have a look at. And the type of file that I'm going to produce is something called an XYZ file. An XYZ file, just to give you, I'll show you over here in a window what an example of that file would be. Oops. So I think this was desktop, temp, oops. To remember where I am in my directory tree. Oh, here we go, sorry. Temp. What I'm going to do is I'm going to write an XYZ file by hand to show you what the format looks like, and then we're going to code up in here so that you can actually automatically generate one. So this is my example .xyz file that I'll show you. So the first line tells you how many atoms you have in your system, and in this example it's going to have 2 atoms. The second line is a blank line, and then here I just give the coordinates of my atoms. So I'm going to name my atom X, and I'm going to put one at 0, 0, 0, and I'm going to put another atom at 0, 0, and we'll make it 3.0. And I'll save my file. I hit ls, I can see my file. Now I need something to actually visualize the file. So let's see if I can open this. So I have, you were given a program called VMD. So I'm going to open the program VMD on my computer. You can either do it from the command line, or if you're using a Windows machine, it's somewhere in your start menu. And then I'm going to go File, New Molecule, Browse, and then I'm going to go find that file that I need. So I think in my case it's called temp. Okay, good. So I found my file. I click here and I'm going to open it. So it automatically knows that it's an XYZ file, and I'm going to go Load. And you can see that it showed up over here in the window. And if I now click on this window, I see, okay, good, these are my two atoms, right? So there's one here and there's one there. So it behaves the way that I expected it to. Now I'm going to click on this guy, right-click on it, and delete the molecule. Because what we're going to do now is we're going to have our code here, the source code that we wrote, and I'll just sort of minimize VMD so it gets out of our way. What we're going to do is modify our source code so that it automatically generates the correct number of atoms. We're going to, that it automatically generates an XYZ file. So to do that, I need to do one thing, is I have to create a file that VMD can write to. And the way I do that is I go output file, so I name the stream, output file is equal to open, and let's call it scc.xyz. And I'm going to open that file for writing, and now I can write to the file as I like. So I'll go output file dot write, and for now let's just pretend that it's going to write 2 atoms. So I go 2 there, and then I use a backslash and an n. This little backslash character tells the computer that hit enter after you're done writing 2. And then I'm going to go output file dot write, a blank line where I also do an n. That little invisible n is my output hit enter. Okay, now here in my code, rather than go print r, right, which I've commented out, I'm going to do the following. I will write output file dot write, and I'm going to put a little x here, okay, with my quotation marks. Notice how I did not put the little return symbol. And then I'm going to write on the next line, output file dot write str, so that means string, r of 0, because r, remember, is an array. When we printed it, we saw that it was an array. R of 0, so this is the first element of r, plus a space, plus str, so converting it to a string, r1, so the second element of r, plus a space, plus str, and r2, which I will then end with a return sign. And actually, you know what? Honestly, there's no point doing these two things on separate lines, so I'm going to put my x out in front. X with a space, plus. So each one of these little guys is a string, and I have these spaces in here so that I can see. Oh, I forgot to close my brackets. Let's close off my brackets here. Okay, it looks like it worked. And then finally, when I'm done, I'll go output file dot close. This is an important thing, otherwise the file system doesn't necessarily know what to deal with the file. Get rid of this, hide that off to the side, and now I'm going to come back over here where I've been running things, and I'm going to go Python scc. Actually, I'll get rid of this. So now you can see that it runs, and because I'm not printing to the screen, nothing comes out of my terminal here. So let's go over to this little window, and we'll see, are there any files? Ah, wonderful, there is a file. It's called scc.xyz. So we have a look inside it using something like more, scc.xyz. I hit enter, and look, I see this string of numbers here. So x, those are my numbers that I expected. Fantastic. Now, one problem that you might have noted is that I just put the number 2 here, right? I coded that in by hand. Really, we'd like our code to generate the correct number of atoms automatically, so that I don't, well, I mean, what could you do at this point? So one thing you could do is you just could sort of count these lines here, right? So let's go through and count these lines. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 23, 24, 25, 26, 27, 28. Okay, what do we got? 27? Okay, 27 sounds correct. So what we could do is you could just count those lines by hand, put a 27 here, all right, there, and then save it. And just to see that it's a valid file, we can open this up. I'm going to open it, scc.xyz, open that, load it. Oops, VMD quit. Oh, that sounds bad. Let's give that another go here. Try that one more time. So we go browse. Hopefully VMD doesn't quit on us. What's going on here? Sometimes computers don't work the way that you want them to. Oh. Haha. Okay, let's fix that little problem. We put too many numbers. Okay. The other thing I just realized is that actually this isn't an SCC anymore, right? Because we changed the lattice vectors. So just so I don't feel bad, we're going to change the name of this thing. So we'll move it from SCC XYZ to something.xyz. Okay. And then I'll open up VMD again. Hope that this doesn't crash and burn. Browse here. Something.xyz. Right. We're going to load this thing. Ah, okay. Excellent. And now I can click on this and rotate. Ah, very interesting. Okay. So far, we're looking pretty good. I seem to have created a crystal. It seems to be something other than an SCC crystal. And I don't know if you can tell very easily what it is. One thing that you can do with VMD to make things a little easier to visualize is if you click on display and switch to perspective, you will get something that looks a little more sort of 3D-like. And then you can figure out, how to classify this thing. Okay. So let's, for the sake of sort of simplicity, we'll go back to our code here. I'm going to bring these guys back in. I will comment out these ones here, save it, and now I feel okay calling this thing a simple cubic. So then we go back over to this window, I rerun it, we'll see XYZ, okay. And now I get an actual simple cubic lattice. Right, but we still have this problem with it too, because it's writing out this 2 that I've hard-coded. Now, of course, at this point, I could write, 27 here, I suppose. But that doesn't feel very satisfactory, right? Because computers are very good multiplication and adding machines, so this thing should do it for ourselves. So one way I'm going to modify my code, or 2 ways I'm going to modify my code, is I'm going to get rid of this number 3 here, and I'm going to replace it with a variable. And I'm going to call that variable nx. All right? And then I'm going to do the same thing here. I'm going to call this y. Actually, no, that's a bad name. na1, na2, na3. There we go. And then back up here, I'm going to give values for those variables. So here's na1. Here's na2, here's na3, and we'll just stick to the 3 that we had before. And here, rather than writing just this hard-coded 2, I can actually just have the computer do some math, which is, we know what value this is going to take. It's going to be na1 times na2 times na3. I have to go plus a space, there we go, plus this little escape character. So we'll save this. We'll run it, and then we'll look over here and see what we get. Ah, perfect. So here, everything looks the same, right? It's still 27 in these numbers, except for the fact that the computer actually calculated this by itself. And now I have a simple cubic lattice. So let's make sure that VMD sees that. So new molecule, browse, scc.xyz. Load it, we'll have a look, and lo and behold, we get the simple cubic lattice that we wanted. Now what happens how do I make a larger crystal? Well, now I can just vary these numbers here, so let's do something really big. We'll say 30 by 30 by 30. Right, I save it, I run it over here in this little window, and then I can have a look to see what it looks like. And oh my goodness, so what is that? 27,000 atoms. So this is a really big file now, right? I'm scrolling through this file. And let's see what VMD thinks of 27,000 atoms. By the way, you don't have to keep closing VMD. I just have this habit where I do that. You can delete the old molecule and load a new molecule. Or you can open it, whichever you prefer. So I go browse. I grab hold of this guy, this scc.xyz. This something thing is from before. It's still kicking around. I'm going to open that. I'm going to load it. And look at this. Now I have a much larger lattice. Also of a simple cubic form. Okay, so just to review what we did, we wrote some code. I'll close this off now. Well, actually, no, I'll leave it open. We wrote some code in one window using an editor, so you could use Notepad or VI or Emacs or anything you like. And the code worked first by starting with NumPy. I then set some values for how many iterations of each, or rather cells I want to go in each of these primary directions. I define my directions, the lattice factors, A1, A2, A3, just like we did in class. Here's an alternate set of lattice factors. Remember, each Bravais lattice has its own corresponding set of lattice vectors. I created an output file called scc.xyz, which I opened for writing. I wrote the first line of that file. I did some math based on these guys here about how many particles there'd be in the file. The second line is blank. In fact, I don't even need that space there. I can remove that. And then I just had 3 for loops. So the first one goes over this integer, this goes over this integer, and the third goes over this integer. I remember what I wrote down in class. I said that this is the value of r. So r becomes now a vector. And then I output for each one of these integer values the x, y, and z component of r. And then I close my file. So that's the end of that. Now, one other thing. I mentioned the fact that you can do this without NumPy. And I will, I'm going to clean up a little bit around here. So I'm going to get rid of something.xyz and example.xyz. And I'm going to get rid of this guy. And just for safety, I'm going to make a copy of this one. So we'll call this no numpy. scc no numpy.py. Oops. To scc no numpy. Let's edit this one. So this is what you could do if you don't have NumPy installed. I would highly recommend that you install NumPy. It should be as easy as either, if you have a Linux machine, it should be something like sudo apt get install either NumPy or Python NumPy. Or if you have OS X, it would be brew install NumPy or Python NumPy. It's something like that. Very useful. And standard tool, frankly. So this is going to be the one without NumPy. How shall I do this? Well, actually, this one's a bit more of a pain.
Time to stand up.
I have to think about it. So for SCC, it's pretty simple. I get rid of these A's, delete all this stuff. Keep this stuff the same. And here, right, what am I going to do? So I can go 2 and 3. Get rid of this R. Okay, R should look the same. Save this. Give it a run. We'll go Python. So I have no files, so I'll go Python scc no numpy. Whoop. I got a mistake here. What did I do wrong? Oh, I see. Right, that's completely wrong. This R is not the way to do this. Sorry about that. So here I have to go string of n1, string of n2, and string of n3. Let's try saving that, because now these are just integers that I'm looping over. I run it, Here's my XYZ file. Let's have a look inside. And I get the values that I expect to get. So for an SCC crystal, it's pretty straightforward to do this without NumPy. Once you get into different lattice vectors and this kind of stuff, in principle you can do it, but to be honest with you, it's a huge pain. So we just use NumPy because we're basically adding and subtracting vectors from one another. Okay, so that's my little introduction on how to tackle this problem of plotting and visualizing these things. And if you have any questions, please let me know.